Welcome back, everyone. In this video, we're going to begin our discussion of electromagnetism. And we're going to start by talking about magnetic flux. So, what is magnetic flux and how do we use it? So you might recall in a prior lesson we talked about the magnetic flux of a magnetic field passing through an area A. And so magnetic flux is simply the product of the magnetic field with that area. You could think of it as the total magnetic effect on a coil of wire of a given area. So you get the maximum flux when the area vector A is aligned so that a perpendicular to this area points parallel to the field. In other words, here is the area, and the area vector A, which is equal to A n hat, is parallel to the magnetic field. You get minimum flux when the area vector is perpendicular to B, and you get intermediate at any angle in between. So mathematically, we say that flux is BA cosine theta, where phi b is the magnetic flux in Webers, which is Tesla meter squared. B is the magnetic field in Teslas. A is the area in meters squared, and theta is the angle between the area and the magnetic field. And so you might recognize that this is just another way of stating the dot product. So the dot product of magnetic field and area is the magnetic flux. So let's try an example problem. Let's calculate the magnetic flux through a rectangular wire frame that's 3 meters long and 2 meters wide if the field is 4.2 millitesla. That's 4.2 times 10 to the negative 3. So in part A, we want to assume that the field is perpendicular to the area vector. So that means that perhaps the area vector is like this. So the rectangular area points like this, and the field goes like this. Since B is perpendicular to A, that angle is 90 degrees, and BA cosine theta is simply 0. So phi B is 0 in that case. None of the magnetic field lines are passing through the area. Part B, same thing, but now if we have an area vector here, we have a magnetic field parallel to that. So theta is 0 degrees, and phi b is just BA cosine of 0, which is 1, so it's just B times A. And B is 4.2 times 10 to the minus 3, and A is just 6 square meters. So we chug that out and you get 0.00252 Tesla meters squared, or Webers if you want. And then if the angle between the field and the area vector is 30 degrees, then that just means we have an area vector like this, and we have a magnetic field like this at 30 degrees. So we just have BA cosine of 30 degrees. And if you plug and chug that out, you get 0.00218 Webers, or Tesla meter squared. So that's a pretty simple example. And we're just using the definition of magnetic flux, which is BA cosine theta. Okay, so here's another example. Here's our diagram. We're going to assume that the angle here is 40 degrees between the magnetic field and the area vector. The magnetic field has a strength of 50 millitesla, and the flux is equal to 250 milliwebers. So therefore, what is the radius r of the loop? Okay, well, so flux is equal to BA cosine theta, and A is actually pi r squared, and then cosine theta. So if we want to solve that for r, we just do a little substitution. We're going to get phi b, which is the magnetic flux, divided by b pi cosine theta, and we take the square root. Plugging in all our numbers, which I encourage you to pause and do, we get about 1.44 meters. Okay, so that's a very simple and quick introduction to what magnetic flux is. And in the next part, we're going to be looking at what happens when the flux is changing.